A potential situation where you'll need to be able to solve multiple angle trigonometric equations is in the application of projectile motion. Now, a projectile is anything that is launched in a gravitational field that follows a parabolic path. To visualize this, I'm going to take our usual XY ordered plane and rotate it around a bit so that you can see a three-dimensional coordinate system here. Let's suppose that we launch some sort of projectile from the origin into quadrant 1. The complete distance traversed by that projectile can be modeled by D, and the XY coordinates of the landing point of that projectile can be given as this distance x, and then relative to our y-axis, this distance y. The distance d in feet traveled by a projectile fired from the ground with an angle of elevation of theta is related to the initial velocity v0 in feet per second by the equation v0 squared sine of 2 theta equals 32d. Notice we're dealing with a multiple angle trigonometric equation. If the projectile is fired from the origin into the first quadrant, then the x and y coordinates in feet of the projectile at time t in seconds are given by x equals v0 t cosine theta and y equals negative 16t squared plus v0 t sine theta. You're certain to see those in your near future in physics and calculus classes. Let's check out example 7. A soldier is accused of breaking a window 3,300 feet away during target practice. If the muzzle velocity for the M16 is 325 feet per second, then at what angle would it have to be aimed for the bullet to travel 3,300 feet? To answer the question, we can use the given equation v0 squared sine of 2 theta is equal to 32d. The muzzle velocity is 325 feet per second. We can plug that in for v0. Notice v0 is squared. So we have 325 squared sine of 2 theta. Theta is our unknown angle here. That's what we're trying to find. And we can set this equal to 32 times the distance traveled, 3,300 feet. To answer this question, we need to solve for the angle theta. So first begin by dividing both sides by 325 squared. Now I'm not actually going to carry out these calculations now. I'm going to do it all in one step with my calculator here in a minute. So I'm going to leave the product in the top and the 325 squared in the bottom. Then we can solve for the angle 2 theta by applying inverse sine to both sides. So we have inverse sine of 32 times 3,300 divided by 325 squared. Let's go ahead and evaluate this with our calculator. Now, since we're dealing with an application and degrees are generally easier to visualize, we'll switch our mode to degree mode. Let's evaluate inverse sine of 32 times 3,300 divided by 325 squared. So the approximation for our angle is to the nearest tenth, 88.8 degrees. So 2 theta is equal to 88.8 degrees. However, let's use our training and practice in solving multiple angle equations to make sure we thoroughly answer and analyze this question. Sine is positive in quadrant 1. Our first solution from the calculator is 88.8 degrees, but sine is also positive in quadrant 2. I can find this other angle by subtracting the reference angle 88.8 degrees from 180. 180 minus 88.8 degrees gives us also a possibility of 91.2 degrees. So the first value that came out of the inverse sine function was 88.8, but we can recognize, based on our knowledge of the unit circle, that 91.2 is also a feasible solution. Now, let's find theta by dividing all of those angles by 2. One possible solution is 44.4 degrees, and 91.2 divided by 2 gives us 45.6 degrees. So in order to cover the distance of 3,300 feet, the initial firing angle could either be 44.4 degrees or 45.6 degrees. Both of those possibilities would cover a distance of 3,300 feet. However, one has an initial firing angle of 44.4 degrees, and the other one has a slightly higher firing angle of 45.6 degrees. The first option would not travel as high vertically. The second one would travel a little bit higher vertically, but they would still cover the same horizontal distance. Let's see if we can answer the next problem. Similar situation. If you were accused of firing an M16 into the air and breaking a window 4,000 feet away, what would be your defense? Well, from the previous problem, we know that the initial velocity of an M16 is 325 feet per second. We'll use that parameter on this problem as well. We also know that the relationship between the distance traveled and the initial velocity is v naught squared sine of 2 theta equals 32d. Replacing v naught with 325, we get 325 squared equals sine of 2 theta times 32d. Before we deal with this distance, let's see what the maximum possible distance of this M16 is. Notice that the distance is equivalent to the product of this positive number and sine of 2 theta. If we want to figure out the biggest possible product, we're going to need the maximum value for sine of 2 theta. Recall that the range of sine of theta is -1 to 1. So this will be maximized when sine is equal to 1. Well, sine of 90 degrees gives us our maximum value of 1. If we're looking at the angle as 2 theta, this means sine of 2 times 45 degrees is equal to 1. So 45 degrees is going to give us our maximum distance. Using that maximum value, we could say 325 squared times sine of 90, which is 1, equals 32d. We can then solve for the maximum distance. That is the muzzle velocity squared divided by 32. And by the way, 32 is related to the value of gravity in feet per second squared. So if we take 325 squared divided by 32, we get a maximum distance of 3,300.8 feet. 3,300.8 feet is the maximum distance for this M16. We could then make the observation that since 3,300.8 feet is the maximum firing distance for the M16, the soldier is innocent, right? He was accused of breaking a window 4,000 feet away. We know that the maximum possible distance reached by this M16 is 3,300.8 feet, so he could not have possibly broken the window. If we compare this to the previous example, notice the window was 3,300 feet away, and this was accomplished at angles very close to 45 degrees. 45 degrees achieves the maximum distance of 3,300 feet. Slightly off of those two angles reaches a distance of 3,300 feet. Let's try example 9. A center fielder fields a ground ball and attempts to make a 230-foot throw to home plate. If he commonly makes long throws at 90 miles per hour, find the two possible angles at which he can throw the ball to home plate. Then find the time saved by choosing the smaller angle. Before we solve this problem, we need to observe that we have two different units given. Here we have feet, and here we have miles per hour. The equation that we're studying, v naught squared sine of 2 theta equals 32d, deals with distance in feet and time in seconds. So we first need to convert 90 miles per hour into feet per second in order for our equations to work. So let's use our dimensional analysis skills and convert miles to feet. In 1 mile, there's 5,280 feet. And in 1 hour, there's 3,600 seconds. Notice how the miles cancel. Notice how the hours cancel, and our remaining units are feet per second. So with our calculator, we could multiply 90 times 5,280 and divide by 3,600 seconds. And we end up with a nice, neat 132 feet per second. This is our initial velocity, or v naught value. Let's plug this information into the given equation. We have v naught squared. Now we're going to use 132 squared times sine of 2 theta. Our angle is unknown. The distance traveled by the baseball is 230 feet. That's the projected distance. We want to figure out at what angle could he achieve that distance. So let's isolate our trig function by dividing both sides by 132 squared. And again, I'm going to postpone all the calculations to the calculator in one step. Then we can solve for 2 theta by applying inverse sine to both sides. So 2 theta will be inverse sine of 32 times 230 divided by 132 squared. With our calculator in degree mode, we'll obtain inverse sine of 32 times 230 divided by 132 squared. Our first observation, we can just go to the nearest tenth here, is 24, well, we'll have to go 25.0 degrees. So 2 theta is 25.0 degrees. However, recall the problem indicates that there's 2 possible angles where this can occur. So let's make use of our unit circle to envision these 2 angles. Sine is positive. In quadrant 1, we obtained an angle of 25 degrees, and that functions as our reference angle. But we also know that sine is positive in quadrant 2. So if 25 degrees is our reference angle, we can take 180 minus 25, you probably don't need a calculator for that, to see that we get 155 degrees for the second possibility. Notice that this is for the angle 2 theta, and we're looking for the angle theta. So we've got one more step here to solve for the angle. That is, we need to divide our answer by 2. So theta is 12.5 degrees, or 155 divided by 2 would give us 77.5 degrees. So there's 2 possible angles at which the center fielder could throw the ball. The smaller angle is 12.5 degrees, and the larger angle here is 77.5 degrees. Either way, it's going to have an initial velocity of 90 miles per hour, and it will cover that distance of 230 feet. However, you can probably see just by looking at the projectile path here that if he chooses the smaller angle, it's going to get there faster. But we want to know how much time is going to be saved by choosing that smaller angle. Recall from the explanation at the beginning of this section that the x-coordinate, or the horizontal distance traveled by the ball, is given by the formula v naught t cosine of theta. We know the initial velocity is 132 feet per second. We have 2 possible values for theta, and the distance traveled, x, is 230 feet. So we can calculate the time for each of those possibilities. So let's start by setting x equal to 230. We're going to use 132 for initial velocity. T is unknown, and we'll start with our first angle of 12.5 degrees. Solving for t, we could divide both sides by 132 and cosine of 12.5 degrees. So the time required for the smaller angle will be 230 divided by, careful in the denominator here, I need to put it in some parentheses, 132 times cosine of 12.5 degrees. Make sure you're in degree mode here. So the time for that throw would be 1.8 seconds. So 1.8 seconds for the smaller angle. Let's see what that would look like for the shorter angle. So I'm going to have a similar setup, but instead of 12.5, we'll use 77.5. So in solving for t, you can see we'd end up with 230 divided by 132 cosine of 77.5 degrees. On the calculator, I'm just going to do a shortcut. That is second entry. And then I'm going to type over my angle of 12.5, 77.5 degrees. And the time here is 8.1 seconds. 8.1 seconds is time. We're determined to find the time saved by choosing the smaller angle. So if we find the difference between those two times, 8.1 seconds for the larger angle, 1.8 seconds for the smaller angle, that gives us a difference of 6.3 seconds. So by choosing the smaller angle, covering the same distance, same initial velocity, time is saved. 6.3 seconds is a lot of time in the baseball game. So in these examples, you can see how it's important to be able to solve a multiple angle equation in the context of projectile motion.